This is my second presentation about the best methods for converting aldehydes into secondary alcohols. This video is about the use of organoboron compounds as nucleophiles. Boron is only slightly less electronegative than carbon, and organoboranes are weak Lewis acids that are not readily hydrolyzed by water. Simple alkyl boranes react, however, with elemental oxygen and must therefore be kept under some inert gas. Like polar organometallics, organoboranes bind strongly to the oxygen atom of carbonyl groups. Nevertheless, no transfer of simple alkyl groups to the activated carbon atom is usually observed. Instead, upon treatment with alkyl boranes, aldehydes are reduced to primary alcohols. This reduction can proceed by an intramolecular hydride transfer or by reaction of the aldehyde with a borohydride, the latter being formed by thermal dealkylation of the alkyl borane. Thus, simple alkyl boranes cannot be used directly as carbon nucleophiles for the nucleophilic alkylation of aldehydes or ketones. This is, though, not the case for allyl boranes, as we'll see later. One of the few exceptions is the example on this slide. It has been reported that some dialkyl boron chlorides do transfer alkyl groups to non-enolizable aldehydes. Unfortunately, yields attainable with unbranched dialkyl boron chlorides are much lower, and with enolizable aldehydes, only boron enolates will probably be formed. The scope of this reaction can, however, be improved by some catalysts, as shown here. In the presence of 8% of a nickel-based catalyst, simple alkyl boranes do transfer alkyl groups to a broad range of aldehydes, but probably not to ketones. Interestingly, this reaction worked best in water as solvent. Another strategy to enhance the reactivity of alkyl boranes is transmetallation with, for instance, diethyl zinc. Here, a trialkyl borane was prepared in situ by hydroboration, whereby the more electron-rich olefin reacted first, as expected. This borane was transmetallated with an excess of diethyl zinc, and the resulting organozinc reagent was added enantioselectively to hexanal with the aid of a chiral sulfonamide ligand. To prevent the transfer of ethyl groups to the aldehyde, all volatiles had to be carefully evaporated before addition of the electrophile. The main advantages of boranes as nucleophilic alkylating reagents are their ready availability from alkenes and their resistance to protonolysis. Because of their low reactivity, these reagents are also better suited for selective transformations of more elaborate multifunctional aldehydes. Unfortunately, alkyl boranes do usually not react directly with aldehydes and require either transmetallation or a catalyst to react. Further weaknesses include the thermal lability of alkyl boranes, which tend to undergo isomerization or dehydroboration upon excessive heating. Then, most alkyl boranes are sensitive toward oxygen and must be handled under inert gas. Unlike alkylations with alkyl boranes, allylations of aldehydes by allyl boranes proceed readily, without the need of any transition metal catalyst. Occasionally, though, Lewis or Brønsted acids are used to speed up these reactions. The mechanism of most of these reactions is sketched here. First, a boron-oxygen bond is formed, followed by an intramolecular transfer and inversion of the allyl group. In this example, trifluoroacetic acid was needed to increase the Lewis acidity of the allyl boronic acid ester by cleavage of the boron-nitrogen bond. A high yield of homoallylic alcohol was obtained under relatively mild conditions. In this example, a chiral allyl dialkyl borane was used to transfer an allyl group to an enantiomerically pure aldehyde. When the other enantiomer of the allyl dialkyl borane was used, a complete reversal of the diastereoselectivity was observed. Because of their low basicity, allyl boron derivatives do not usually racemize aldehydes as the one of this example. The non-chiral allyl boron pinacolate, for instance, would probably not racemize this starting aldehyde, but its diastereoselectivity is much lower than that of the terpene-derived allyl borane. This example shows that allyl boranes are usually more reactive toward aldehydes than allyl silanes. This is because boranes quickly bind to the carbonyl oxygen atom of aldehydes, whereas allyl trialkyl silanes do not form such bonds. Let's now have a look at the arylation of aldehydes. Aryl boron derivatives do not usually react with aldehydes unless some transition metal catalyst is used. Palladium, nickel and rhodium-based catalysts seem to be best suited to bring about this reaction. Alternatively, as with alkyl boranes, a further way to activate aryl boron derivatives is by stoichiometric transmetallation with diethyl zinc. This is an example of the nucleophilic arylation of benzaldehyde with an aromatic boronic acid. Potassium phosphate was added to turn the reaction mixture more basic and thereby the boronic acid into a more reactive potassium boronate, as shown on the previous slide. 5% of a nickel-2 catalyst was sufficient to attain a high yield of secondary alcohol. As alternative to boronates, trifluoroborates can also be used as arylating reagents. In this instance, the reaction was biphasic with 1.5% of a rhodium catalyst in the organic phase. In this example, the starting phenylboronic anhydride was transmetallated stoichiometrically with an excess of diethyl zinc and then treated with 2-fluorobenzaldehyde. Interestingly, zinc transfers aryl groups much faster than alkyl groups, and only 5% of hydroxypropylarene was obtained as byproduct. Here, the arylation was conducted in the presence of 10% of an enantiomerically pure amino alcohol, and the expected diaryl methanol was obtained in high chemical yield with 91% enantiomeric excess. This indicates that the phenyl-zinc ligand complex reacts much faster with the aldehyde than uncomplexed phenylethyl zinc. Despite the lower reactivity and increased selectivity of organoboron compounds, if compared to polar organometallics, still a number of side reactions may occur. Secondary alcohols are easily oxidized to ketones, and with some transition metal catalysts, ketones may be formed as byproduct or even as main product, as shown here. Occasionally, aldehydes may also be reduced to primary alcohols by hydride transfer under the reaction conditions required for nucleophilic arylation or alkylation. In this instance, the hydride source was probably isopropanol. Nickel, palladium and rhodium can yield metal acyl complexes upon reaction with aldehydes, and these can decarbonylate by intermediate formation of a metal carbonyl. Such reactions, however, usually require a relatively high temperature to go to completion, but small amounts of decarbonylated byproducts can be formed already at lower temperature. Further side reactions include the copper-catalyzed alkylation or arylation of various heteroatoms by boranes. This includes the alkylation of amines at nitrogen, the arylation of alcohols and phenols at oxygen, and the O-alkylation of carboxylates. Boranes may also undergo conjugate addition to alpha-beta unsaturated aldehydes or other electron-deficient double or triple bonds. As already mentioned, alkyl boranes cleave off olefins upon heating, and hydroboration of these olefins can yield isomerized alkyl boranes. In fact, prolonged heating of alkyl boranes can yield complex mixtures of isomeric boranes. Copper has also been shown to catalyze the reaction of diaryl methanols with aryl boronic acids, and triaryl methanes may be obtained as byproducts if benzaldehydes are treated with an excess of aryl boronic acid. Finally, organoboron compounds are much more resistant to oxidation and hydrolysis than polar organometallics, but can be hydrolyzed and oxidized under forcing conditions. Here, I've listed a few more recent examples of the use of boranes as carbonucleophiles for aldehydes. Some of these conditions can also be used for converting ketones into tertiary alcohols, but most ketones are significantly less electrophilic and sterically less accessible than aldehydes. In the next video, we'll have a look at the use of silanes as carbonucleophiles. See you then.